half-life is a relatively easy concept to understand. Half-life is defined as the amount of time required for the nuclear decay process to occur for 1/2 of the particles present. So in this example, we're going to start off with 400 particles. After the first half-life, we're going to end up with 200 particles. And in this sample, this example, I went ahead and used a time unit of 10. So the T sub 10 represents 10 minutes. And after that 10 minutes, we have 200 particles left. After the next half-life, which is going to be another 10 minutes, or a total of 20 minutes, we're going to have only 100 particles left. Now, notice one thing here that we've got. Each half-life is 10 minutes long. So no matter what we have, no matter how much material we are starting with, we are always going to have the same amount of time required for half the material to go away. So in our third half-life, after a total of 30 minutes, we're only going to have 50 particles. And in our last or fourth half-life, we're going to have a total of 25. So in each time increment of 10 minutes, we have lost half of the material that we started with. Now the calculations for these are relatively straightforward. There's a little bit more to these equations than what we're going to cover, but we can use these equations at face value to do some fairly basic calculations. The first equation is showing the calculation for what the actual half-life is. And this is one of those equations where there's a lot more going on in the background, and this is the final result. Suffice it to say that K is the value K is the decay constant, and that's a measure of how quickly the material is going to be decaying. If that is measured, we can then calculate what the half-life is. In any problems that you would be given, if you need to use K, you would be given the value of K to calculate that half-life. In the second equation, the N sub T represents the amount of material that is left after a certain amount of time, T, has elapsed. So in our previous example, T would have been, our first half-life, our T would have been 10 minutes. So N sub T would have been the amount left over after the first half-life. N sub 0 is the amount of material that we start with, the initial value of material that we start with. So again, in the previous example, T sub 0, our N value would have been 400. After 10 minutes, our N sub T, or N after 10 minutes, would have been 100. Let's look at how these equations can be used. Here we have an example using a radioactive material with a K value of 0.0693 and a sample mass measured to be 3.28 times 10 to the third grams, or 3,280 grams. After 3 hours, what will be the mass of the sample? So to start off, we're going to have to calculate what the half-life is because we're not given that value. We're going to need to use the K value, and it has the units of 1/minute, which seems like a strange unit, as you'll see, but you'll see why here in a second. So we're going to have T 1/2 equals 0.693 divided by K. And if we plug that in, we're going to see 0.693 divided by 0.0693, 1/minutes. If we solve this out, we're going to end up getting 10 minutes. And a unit of 1/minutes is required so that we have our math work out properly to get the unit of minutes in our final answer. So our half-life is going to be 10 minutes. The other problem we have right now is that we're given a time in hours, but we want to know our half-life is given in minutes. Now these two units must match up, so we're going to convert the hours to minutes. So 3 hours times 60 minutes in 1 hour, and that's going to give us 180 minutes. And now it's just a matter of plugging into that second equation that we were given. If we use the equation N sub T, where T, this is going to represent the amount after our 3 hours, equals 3.28 times 10 to the third times 0.5 raised to the 180, that would be our time, divided by 10, and that will equal 0.0125 grams.